Let's dive right into this explainer and uncover the invisible architectural rules holding the physical matter of our entire universe together. I mean, we interact with physical stuff literally every single second of our lives, right? But we rarely stop to think about how it's actually built from the ground up. Today, we're zooming way in to look at the covalent bond. And really, at its core, this is all about a magnificent quest for stability.
Think about a simple, beautiful water droplet resting on a leaf. What's absolutely fascinating is the invisible quest for stability happening right inside it. To us, it just looks like water. But chemically, we're looking at a massive, interconnected network of hydrogen and oxygen atoms holding onto each other for dear life. And that brings us to a pretty fundamental question about the very nature of matter.
Why aren't atoms just happy totally on their own? Why do they even bother bonding at all? Well, the answer really just comes down to achieving a stable, lower-energy electron configuration. You see, atoms are inherently lazy, but in the best way possible. They just want to exist in the lowest possible energy state. It's like they look over at the noble gases, which naturally have those perfectly full outer energy levels and low potential energy, and they think, yeah, I want exactly that kind of stability.
So here's our agenda for today. We'll start with the quest for stability, map out finding the perfect balance, move on to drawing covalent bonds, then look at sigma, pi, and multiple bonds, check out bond length and strength, and finally, we'll examine energy in chemical reactions.
Section 1. The quest for stability, and exactly why atoms bond.
Section 2. Finding the perfect balance and the forces at play.
To really understand how atoms solve this instability problem without literally just crashing into each other, let's picture two fluorine atoms. As they get closer, this fierce microscopic tug-of-war kicks off. On one side, you have repulsive forces. Their like-charged protons are pushing apart, and their electron clouds are pushing apart too. But battling against all that repulsion, you've got attractive forces, where one atom's protons are pulling hard on the other atom's electrons. So they keep moving closer and closer until they hit this perfect sweet spot. It's the exact point of maximum net attraction, because if they get even a tiny bit closer than this, repulsion just completely takes over. And when they finally lock into that perfect, mathematically precise distance, boom, they form a covalent bond. They start sharing their valence electrons so that both atoms can complete their outer shells. And this shared arrangement is brilliant, because it means those electrons now belong to both atoms simultaneously. It literally ties them together into a stable molecule that has way less overall energy than the two separate atoms had on their own.
Section 3. Drawing the covalent bonds and mapping the electrons.
Okay, so how do chemists actually visualize these microscopic handshakes on a flat piece of paper? Well, we use this simple but incredibly powerful tool called a Lewis structure. In these diagrams, a pair of dots, or just a single straight line, represents one shared pair of electrons. By mapping it out exactly like this, whether we're looking at two fluorine atoms linking up or an oxygen atom grabbing two hydrogens to make water, you can perfectly account for every single electron. It's how we make sure every atom achieves that highly coveted, super stable noble gas configuration.
You know what makes this whole system so elegant? It's the sheer predictability of it. Depending on where an element sits on the periodic table, you know exactly how many single bonds it needs to form to finally reach stability. For example, group 17 halogens have 7 valence electrons, right? So they just need one more, meaning they form one bond. Group 16, like oxygen, needs 2. Group 15 needs 3. And group 14, like carbon, needs 4 whole electrons, so it forms 4 bonds. It is just a remarkably consistent set of rules for molecular architecture. Section 4. Sigma, pi, and multiple bonds, and how these orbitals overlap.
Now, in reality, atoms aren't just bonding on a flat piece of paper, are they? We live in a 3D world, and there are two main ways these orbitals actually overlap in three-dimensional space. Single bonds are always what we call sigma bonds. This is where the atomic orbitals overlap directly end to end, and it concentrates the electrons right smack in the middle between the two atoms. But when atoms need to share more than one pair of electrons to reach their octet, they have to form multiple bonds. And here's the catch. That second or third bond cannot occupy that exact same direct space. So they form what are called pi bonds. These happen when parallel orbitals overlap side by side, creating these wild electron clouds hovering above and below the central connection.
To really see this in action, let's look at the carbon atoms in an ethene molecule. They share a double bond. So right down the middle, you've got your direct sigma bond holding the fort. But because those atoms are being pulled so incredibly close together, their parallel p orbitals start to overlap side by side. And what does that look like? It results in this absolutely fascinating donut-shaped electron cloud just hovering all the way around that central sigma bond. And that right there is your pi bond.
Section 5. Bond length and strength, and the crucial inverse relationship between the two.
So now that we've mapped out single, double, and even implied triple bonds, let's talk about how sharing all those extra electrons actually affects physical size. Take fluorine, for instance, with its single bond. It sits at a bond length of 1.43 times 10 to the negative 10th meters. But then, look at oxygen. It shares 2 pairs of electrons for a double bond, which pulls those atoms much tighter together, dropping the length down to 1.21. And if we go down to nitrogen, which shares 3 pairs for a triple bond, it's packed even tighter at just 1.1. So what we're actually seeing here is a direct inverse relationship between length and strength. As atoms share more and more electron pairs, the bond gets physically shorter. And as it shrinks, the energy required to break that bond apart, which chemists call the bond dissociation energy, absolutely skyrockets. To give you some perspective, breaking that single fluorine bond takes 159 kilojoules per mole. But trying to break that incredibly tight nitrogen triple bond, that demands a massive 945 kilojoules per mole. That is a huge jump.
Section 6. Energy in chemical reactions, focusing on breaking and making bonds.
Now let's take this microscopic concept of bond energy and scale it all the way up to the macroscopic chemical reactions we witness every single day. Think of every chemical reaction as essentially a complex energy transaction. It literally all comes down to a balance sheet of breaking old bonds versus making new ones. If breaking the old bonds in your starting materials costs you more energy than making the new bonds actually pays out, the reaction has to absorb energy from its surroundings. We call that an endothermic reaction. But on the flip side, if forming the new bonds yields a massive surplus of energy compared to what you spent breaking the old ones, it blasts that extra energy outward. And that is an exothermic reaction.
A totally classic example of this exothermic process in action is burning charcoal on a grill. When you first light the charcoal, you are actively breaking the carbon-carbon bonds in the coal, along with the oxygen-oxygen double bonds in the surrounding air. That step requires an initial investment of energy, right? Which is exactly why you have to strike a match to get the fire started. But once those atoms rearrange themselves and lock into their shiny new, highly stable carbon dioxide bonds, they release a massive, massive surplus of energy in the form of heat and light.
It completely changes how you look at the world around you, doesn't it? The next time you're sitting by a roaring campfire feeling that heat, or even just noticing a simple, stable drop of water resting on a leaf, remember what's really happening. You are witnessing the direct results of microscopic atoms finding their perfect balance, massive energy exchanges and invisible forces of attraction happening right before your eyes. It really leaves you to wonder what other tiny, invisible quests for stability are quietly shaping our universe every single second. Thanks for joining me on this explainer, and as always, keep questioning the world around you.